An off-the-charts earthquake took place in a University of Michigan lab in December. Designed to test a new technique for bracing high-rises in seismic zones, the simulation shook a 4-story model building, but after a full day of testing, the building stood tall.
We were favorably impressed, definitely. And really, we were testing this to the maximum credible earthquake, just how far this building might be displaced. And we had a lot of instruments measuring really the lateral force versus the displacement, or if you wish, the drift as a percentage of the height of the building. And we were able to get it up to a load of over 250,000 pounds, peak load up around 300,000 pounds, and it maintained that load out to very large drift levels, as large as 3%. And normally you might expect a building to start deteriorating after drifts of maybe 1.5%. You could have a solid wall, and that would be the best solution. But normally you need openings in this core wall building to get into stairwells or get into elevators. Sometimes if you use the wall at the edge of the building, you have window openings. So we need openings.
These openings weaken the structure. In earthquake-prone areas, builders must reinforce the walls with coupling beams. Today, coupling beams are made of tangles of steel. The U of M engineers created a simpler version, made of steel fiber reinforced concrete.
So what we are doing is taking quite a bit of reinforcement out of a typical design and replacing that with fibers, which can be treated as an additive to the concrete. Basically, you would mix these fibers with the concrete, but then you would cast this fiber concrete in a beam that has much less reinforcing bars. When you have plain concrete and it cracks, there's nothing bridging that crack that will allow it to continue taking tension. So the key issue in terms of the fiber concrete is that it develops or exhibits a strain-hardened response after first cracking. With the fiber reinforced concrete, we can achieve much closer cracks.
Well, we think it's important because the design that we're going through for these coupling beams, it's a much easier design for the contractors to put together in the field. We think the current designs, although they work adequately, are extremely difficult, and we've had contractors tell us it adds quite a bit to the cost of a building putting in these highly reinforced coupling beams. Our designs are much easier. We also are proposing that they be precast, either off-site, they could be precast on-site, but then they can just be brought up as a unit and cast in place with the surrounding walls.
Engineers have been working on this project at Michigan since 1999. Their December experiment was their most significant structural test in the last decade. They applied the largest force the structures laboratory has ever seen.
One of the most unique features of the lab is the reaction wall we push off of to test our specimens and simulate an earthquake. And by simulating an earthquake, I mean we push the wall, our specimen back and forth slowly, but with I guess increasing displacements, and just observe how the failure happens. And so before we entered the test, it was a very significant earthquake. We ended up moving it more than twice what you'd expect a building of this kind to undergo, I guess, in a large seismic event.
And with respect to life safety under a maximum credible earthquake, we believe this would have been strong enough to hold the building up. People could have evacuated from the building after the earthquake.
So now we are working with a structural design firm on the implementation of this concept into several high-rise structures on the West Coast.
It's a good product.